Hmm?
But just a reminder, please put all your mics off. But before we start today, just please make a note that there's no 8 p.m. lesson tonight. I have a group of grade 10s and I couldn't move them out of the 8 p.m. slot. They are all writing a test this week as well. So there's no 8 p.m. lesson tonight. All of you can actually just check your respective groups. I may actually decide to have a lesson between 6 and 6:30 tomorrow, which means I'll put it up late tonight. I finish off at 9 o'clock tonight. So by 9:30, if I can manage the 6 to 6:30 a.m. lesson tomorrow, I'll actually let you know about that. And the reason for this is quite simple. For those of you that are in grade 11, well, even in grade 12, you are essentially writing in 3 weeks. And there's just too much work to complete. And I don't know how your schools are going to do it, but this work just has to be completed. You may just want to put out a message in all your groups, please, that the others should actually attend. So we know we've actually told everyone about this, especially the grade 11s. Grade 12s are generally masters at Newton's laws by now. So if they're not here, it's okay. But the grade 11s need to be here. Right. I've now taken a set of questions that are quite different from the other ones. I want to start off with this horizontal and vertical scenario that we were dealing with. But the difference here compared to the others that we've been dealing with is actually that the tension over here is acting at an angle. I just want to quickly point this out, that the tension in the rope over here that is attached to the 8 kilogram is acting at an angle of 15 degrees to the horizontal. So there's your tension there. And that's going to make a bit of a difference to the way we are actually going to deal with the 8 kilogram mass eventually. The 2 kilogram mass is going to have the tension acting upwards there. Again, just please note that because the 2 kilogram mass is actually hanging in the air here, there is no normal force acting on this. Alright, let's go for it. A block of mass 8 kilograms is placed on a rough surface. The 8 kilogram block is connected to a 2 kilogram block by means of a light inextensible string passing over a light frictionless pulley. And it starts sliding from point A as shown. Well, you can't really see it sliding from point A, but I mean, it is sliding. I'm going to leave out the definition for Newton's second law here. You can clearly see how popular Newton's second law is. In Newton's laws, it is the most popular definition to come out. Please ensure that you learn it. Draw a labeled free body diagram for the 8 kilogram mass, and that tension acting at an angle is important now. Now, before we start, I am not a fan of drawing the tension. Sorry, I'm not a fan of drawing a force acting at an angle. I would prefer drawing the components of that force because those components are going to be useful in my calculation. So you will find me drawing the components as opposed to a singular force over there. So my components of my tension are going to be Tx here and Ty here. And then we can fill in all the other forces. So for the 8 kilogram, we're going to have our gravitational force going down, our normal force going up, you're going to have your kinetic frictional force going backwards. There is no externally applied force on this system here. What's unique about this one is that you actually have your tension at an angle. They told us that it's moving across from A to B, so your acceleration here is to the right. So all our vectors pointing to the right are going to be positive, and all our vectors pointing to the left are going to be negative, which means that the 2 kilogram mass, which I'm going to draw the free body diagram for now as well, is going to have your gravitational force acting downwards, and that's going to be larger than your tension force T acting upwards. There's no component here for that tension. It's just the singular tension acting along the string. And because the 8 kilogram is accelerating across from A to C, this is going to be accelerating downwards here. So there's our 8 kilogram free body diagram. And there's the 2 kilogram free body diagram. All right, when the 8 kilogram block reaches B, the angle between the string and the horizontal is 15 degrees, and the acceleration of the system is 1.32 meters per second squared. So they gave us the acceleration. Give a reason why the system is not in equilibrium. Anybody wants to answer that? Why is the system not in equilibrium? From Newton's second law, your acceleration is directly proportional to your net force. And if the acceleration is not equal to 0, that means the net force is not equal to 0. If the net force is not equal to 0, the system is not in equilibrium. The system is only in equilibrium if F net is equal to 0. I'm glad that I actually see a few more of the grade 11s from my group over here. I'm hoping that the rest of them are actually going to come. Maybe somebody in the grade 11 group from DHS puts up a message for me, please. Thank you. Use, and this examiner was really kind, because normally they don't do things like this. It says use the 2 kilogram mass to calculate the tension in the string. And they've only given 3 marks for this. So there's our 2 kilogram free body diagram. It's accelerating downwards. So the gravitational force is the positive force. The tension is the negative force. We're going to use F net equals MA, and we're going to calculate that tension. That's 13.3.2. So for the 2 kilogram, your tension is going to be Fg, which is the positive force, plus minus the negative force, your tension, equals to Ma. That's Mg minus your tension equals Ma, and we got the acceleration. 2 times 9.8 minus your tension is equal to 2 multiplied by, please don't forget we have the acceleration of 1.32 meters per second squared. That's 19.6 here. Take the t across, it becomes plus t. 2 times 1.32 is minus 2.64. The answer for T, please?
15,96, sir.
15,9, sorry,
16.
16,96, yes. They would normally ask you to calculate the magnitude of the tension, eh? I'm just going to say upwards from the 2 kilogram. But I'm almost certain if you look at the memo, there's no direction given here. I'm putting this in brackets because I don't think it's necessary. It's very rare that they would ask you for a direction for tension because the tension is always acting in different directions. Now that we've got the tension sorted out, we can actually answer the questions that follow after that. It says calculate the kinetic frictional force on the 8 kilogram and the horizontal surface. Did they give us a coefficient of friction? Let's have a look. No, they didn't. Which means we can't use Fk equals mu k times n, but we can use the following. What we can use are these two horizontal forces here. And we know that because it's accelerating to the right, the force to the right is positive, and this Fk here is negative. So 13.3.3. This is now for the 8 kilogram mass. F net equals ma. Be very careful, yeah? It's not your tension, it's the x component of your tension minus the kinetic friction is equal to ma. And Tx is T cos theta minus your kinetic friction equals ma. I'm going to move this. I need a blank page here. Okay, put that up there. Right, our tension was 16.96. Cos of 15 degrees. We don't know the Fk here, so minus the Fk again. Your mass is 8, and they gave us the acceleration. Thankfully, we didn't have a simultaneous here. So take that across, you'll get your kinetic friction. So 16.96 cos 15 minus 8 into 1.32. Anyone's got an answer for the kinetic frictional force?
5,82.
Thank you. So here we have to put a direction. So it should be to the left. Oh, sorry. Let's go back there. Yeah, it's to the left. And then, as the 8 kilogram moves from B to C now, that means it's getting closer to this point where we've got this rigid rod here and a rigid pulley over there. Now, in this scenario here, you don't have a hand pulling on it, on a string, moving it upwards. You also have a scenario where, as it's going to reach some point over here, maybe close to C over here, this entire system will start lifting upwards because this pulley and this rod is rigid. It's going to force this 8 kilogram off the surface there. As the 8 kilogram moves from B to C, the kinetic frictional force between the 8 kilogram block and the horizontal surface is not constant. Give a reason for the statement. And then the main reason for this is because as this actually moves from B to C, here in this unique situation, it doesn't happen all the time. This 8 kilogram is going to start lifting off the surface, which means the normal force is going to decrease because the surface is not going to be in contact with the block anymore. There'll be less contact between the surface and the block, so there'll be a smaller normal force being applied. Eventually, if it goes completely off the surface, which it won't, right, there would be a zero normal force. So the normal force decreases as it moves from B to C because the box moves slightly off the surface. So 13.4, your kinetic frictional force is equal to mu k times n, which means your kinetic friction is directly proportional to your normal. As it moves from B to C, it lifts off the surface. Therefore, normal force decreases. Which implies Fk decreases. And here's a very nice question to finish this up. The horizontal surface on which the 8 kilogram block is moving is replaced by another horizontal surface made from a different material. Now, if you change the surface, you change the coefficient of friction. The mu k will change. And if that changes, the kinetic frictional force will definitely change. Will the kinetic frictional force calculated in 13.3.3 above change? The answer is yes. And the reason for that now is the mu k value changes. Why? Because you've replaced the surface here. Surface changes. Therefore, mu k changes. Therefore, Fk changes. And the reason why your Fk will change is because your Fk is also directly proportional to your mu k from the equation here on top. The bigger your mu k value, the bigger the kinetic frictional force. Now, before I go any further, I just want to also, I think I need to tell you or explain to you why we're having all these lessons bunched up so badly. This is for the grade 11s. If we do not plan this in advance and do all these questions intensely for both Newton's laws and electrostatics, and you are then suddenly saddled with one of these weird questions in this section, either now in grade 11 at the first term, or in the June exams, or in the final exams, or next year in the first term, next year in the June, and next year in the trials, and next year in the final. So you can see how many times Newton's laws are going to come out. It's going to come out in 6 other exams, not just this first one. You have to be ready for all of them. If we do it badly, if we rush through it, and that's what most of the schools are going to end up doing, you are never going to get a full understanding of all the different scenarios you could get with all the weird complexities attached to it. And then you'll be wondering how you start working out all these questions. Now, this is mainly for my grade 11s than for the grade 12s, because your exposure is limited compared to the grade 12s. The same is going to happen for electrostatics, which is going to start on Friday, by the way. Right? I'm going to start off with Coulomb's law on Friday. And I'm hoping to actually finish quite a few different examples by Sunday. and I'll only have electric fields left for that following week and a half or so before you write. Please attend. I've planned this out knowing you are writing early and knowing the volume of work we need to complete. If I'm willing to make up or give off my time, please make sure that you are also going to do the same. I'm going to put up a notice on both the grade 11 groups. Please have a look at it. And please make yourself available. It's not going to be the easiest of things. And tomorrow, when I do continue with some of this, I'm just going to assume that you know all that we've done so far. So it's not going to be a case where we're going to be rehashing all of this because the videos are available and I'm hoping that they've been posted somewhere. Right, the next question. This question here came out in the 2023 supplementary exam last year. So it's an extremely recent question. It's a question that only involves objects that are moving vertically. So there is no horizontal motion here. There is only vertical motion here. This is a rarity where they give you both objects moving vertically. It hasn't come out very often. And when this question came out last year, and a similar question like this came out during the trial exam, it actually messed the learners up very badly. Actually, there was a large number of educators which basically protested against a question like this being set because it wasn't actually of a standard that would have been acceptable to a grade 11 class, especially. Now, somebody asked me, and I'm going to just emphasize this again. Can these questions which appear in grade 12 papers appear in grade 11 papers? The answer is yes. There's no difference between the 11 and 12 work. So please get ready for this. Okay, so before we start, what are the little complexities that you need to remember here for vertical motion that's different from the other one? Here, because we've got both the masses that are eventually going to move in the air, both of them will have no normal force on them. And the other thing is, because they're both moving vertically, you're only going to analyze the vertical forces here. There's going to be no horizontal forces on these two masses. So the vertical forces are going to be responsible for the vertical motion of these two objects. The other thing that's important, somebody left, I hope they come back, is the direction of the motion. How are you going to know what direction they move here? Well, here it's a bit hard because you got an unknown mass here and you got a 7.5 kilogram mass there. But the question will tell you how they move. Let's read. Block A of mass M is connected to block B of mass 7.5 kilograms by a light inextensible rope. Let me talk about that rope. You are going to have your tension in your rope acting towards the pulley, which means both your tensions are going to be acting upwards. Because it's the same rope, it's the same tension. Block B is initially held. That means that your initial velocity here is 0. At a height of 1.5 meters. Now, you may be wondering why did they give us a height here? Because you're going to use an equation of motion from grade 10 here. Your delta x here is 1.5. Above the ground, whilst block A is initially stationary on the ground. When block B is released, it moves vertically downwards. So this accelerates down, which means this is going to accelerate up. You need to remember this, that if one accelerates in one direction, the other mass is going to accelerate in the opposite direction. Why is that important? Because here your downward forces are positive for the 7.5 kilogram. For M, the upward forces are positive because this is accelerating upwards. Here's the more important thing, because we haven't done one like this before. It moves vertically downwards and strikes the ground with a velocity of 3.41 meters per second. So your VF is 3.41. Most of the learners got stumped here. Because in questions like this, we normally find the acceleration using Newton's laws, simultaneous equations. It says, show by means of a calculation that the magnitude of the acceleration. Now, this is a good examiner because they have different directions. It's always good to just ask for the magnitude of the acceleration. Magnitude of the acceleration of block B is 3.88 meters per second squared. Now, because these two blocks are connected, they're going to have the same tension, and please note they're going to have the same acceleration as well. Exactly the same like a horizontal scenario, but we have them vertically here. They're going to have the same acceleration on both. While block B is moving vertically downwards. All right, my grade 12s are going to give you this. Watch. Anyone in grade 12, tell them which equation of motion we're going to use to calculate the acceleration here. Don't let me down, grade 12s.
Sir, is it VF squared equals to VI squared plus 2 delta X?
Correct, sir. You're supposed to know this all off by heart, by the way. This is not for the grade 12s only. This is for everyone. Don't tell me you did it last year and you forgot it. You quite likely did, by the way. So a deeper question to ask, which obviously I had this question asked to me last year. Do I actually need to know my grade 10 work for this grade 11 section on Newton's laws? And the simple answer is yes. Because God forbid they actually give us a question where we have to actually use an equation of motion from grade 10 to find the acceleration, and we don't know anything about equations of motion. Then we're going to get stuck right at the beginning. And yes, most of the learners got stuck at the beginning. So it's three. So don't worry about convention and stuff here because this is not acceleration due to gravity grade 12s. So 3.41 squared equals to 0 squared plus 2 into a, which we don't know. And my delta x here is 1.5. So 3.41 squared equals to 3a. What's that, like 3.2 or something? Oh, they gave it the answer. So they gave us the answer. 3.88. Check if you get it.
Yes, sir, we do.
So there's your acceleration. You can try it. The other thing for all these lessons is simply exposure to all the different approaches they can actually use for Newton's laws. And we've done some really, varied questions over the last couple of days. Now that we know the acceleration, 3.88 here and 3.88 there, that's going to help us because we're now going to go for the free body diagrams. I'm going to draw the free body diagram for A and for B. They didn't ask us for A, but I'm going to start off with A. Please note that A accelerates upwards. A is going to have two forces on it. It's going to have your tension acting upwards and your gravitational force acting downwards. It's accelerating upwards. It's stated in the question or implied in the question. B is going to have exactly the same forces. You're going to have your tension acting upwards. But because this is accelerating downwards, the gravitational force on B should be bigger than the tension force. I'm going to leave out the statement. So this was 2.2. I'm going to leave out 2.3, which is again the definition of Newton's second law. Calculate the value of m by applying Newton's second law to each block. So they're giving us a hint here. So let's start off with A, which has the unknown mass m. Because it's accelerating upwards, the upward force is positive, the downward force is negative. So here, F net equals MA. It's your T plus minus FG is equal to MA. We don't know what the tension is. It's going to be minus mg equals to MA. We don't know M, remember that. So that's T minus 9.8 M is equal to, we worked out the acceleration. Remember the acceleration was 3.88 M. So here T equals to 3.88 M plus 9.8 M. What's my answer for T in terms of M here, please?
So 13.68.
13.68 M. That's equation 1. Then for B, where we have the known mass, F net equals MA again. Now this is accelerating downwards. So the downward force is positive and the upward force is negative. See how important it is to know in which direction the acceleration is. By the way, if you did not do these little things here, check the direction of the acceleration, let the forces in the direction of the acceleration be positive and the opposing direction to be negative. If you don't do things like that consistently in every question, you'll get questions like this wrong. They're small things, but they are important. So here it's Fg plus minus T equals to MA. So that's Mg minus T equals MA. What was the mass for this one? 7.5. So 7.5 times 9.8 minus T equals to 7.5 into 3.88 for the acceleration. So take the T across. Okay, so we solve for T here from the second equation. 7.5 times 9.8 minus 7.5 times 3.88, and we got our answer for T. Can somebody solve for T for me quickly, please?
So,
Yes, sir.
so what happens if you just divide the masses instead of substituting? It's like you get rid of the masses and then you left with G minus T is equals to A, sir.
Where, sir?
So for equation B, the third line, instead of
Yeah,
substituting
you can do that, sir, but you can't divide by the mass here where you got T.
oh,
You can't just divide this by 7.5 and that by 7.5. You have to divide the T by 7.5 as well. You have to divide the whole equation by 7.5. So that just won't be wise over here. You're just going to make the equation messy for nothing. It's not that you can't do that, but there's no point in doing that.
okay, thank you,
Right?
sir.
Right.
Got 44,4.
Sorry, say it again.
44,4.
Exactly.
Yeah.
And now that we got the T from equation 2, we substitute it into equation 1 and we solve for M. So 44,40 equals to 13.68 M. 44.40 divided by 13.68.
3,26.
Right, calculate the maximum height above the ground reached by block A. That's 5 marks. Grade 11s, you can actually just switch off here because you won't know the second part of this answer. Let's ask the grade 11s this. This is going to drop down to the ground and it's going to go down 1.5 meters. As this 7.5 kilograms goes down 1.5 meters, what's going to happen to M on the other side? Okay, let me just take this out from here because we're going to need some space again. So what's going to happen to M on the other side? This 7.5 kilograms.
So once it lifts up,
Good. So this is going to go down 1.5 kilograms. Up 1.5 meters. So this is actually going to lift up 1.5 meters. But then something's going to happen once this block gets here. What's going to happen to the tension in the string? That tension in the string is going to go right down to 0. Because this is now on the ground. It's not going to be pulling on anything. What's going to happen at this point here when this goes up 1.5 meters and reaches this point, grade 12s? They didn't give 5 marks for nothing here, isn't it? Grade 12?
so
But
the
wouldn't
system
stop moving, be stationary.
Sorry, just say it again.
The system would be stationary, so it wouldn't be moving.
No, it would. It won't, it can't just suddenly come to rest. Why? Because it's already in motion here at this point. And at that point, when it's actually moving here, there, what are the forces acting on it? There's no tension anymore pulling upwards. What's the only force acting on it?
So it'll just be your FG.
Which means now it's in free fall, isn't it? Which means what's going to happen to it from here going upwards? VPM, guys. Do we know the velocity at this point? Obviously, it's not. It should be the same velocity that this mass acquired over there, isn't it? Which they gave us in the question. But you can double check that it is 3.41 if you don't trust me on this. So that's going to be your VI there. And then what's going to eventually happen to it? It's going to reach a certain maximum height here, isn't it? What's the VF there? 0.
0.
What's my acceleration in the green zone? Minus 9.8. It's in free fall. You want to calculate the delta X. As I said, grade 11s, don't worry about this. Grade 12s, you will. So for the last question, it deserves 5 marks. 1 mark for you to realize that it's not going to actually just stop dead there because it's already moving at 3.41. And how we got that? Because this landed at 3.41 when it went 1.5 meters down. So this has to be 3.41 at that point, 1.5 meters up. VF squared equals VI squared plus 2a delta X. Your VF is 0. Your VI is 3.41. It's 2 into minus 9.8. Delta X. Anyone's got the answer for delta X there? The answer, please. Oh, sorry, I didn't square.
So I got negative, I got 0.59. So
Right, positive, not negative. Huh?
yes, no.
So what's the max height above the ground now? So your max height is the 1.5 there, plus the 0.59 that it additionally went up in free fall. which gave you 2.09 meters. Grade 11s, I hope this gives you a glimpse of what next year is going to be all about. So you used in this question here your grade 10 equations of motion, your grade 11 Newton's laws, and you use your grade 12 VPM here. They tested everything. All in one. That was a good question, eh? Really good. But just give me a second, please. I'm going to start off now with inclined planes, and I've taken a really nice, cool example to start us off. Not a very difficult one. It's a double mass system on an inclined plane. 1 minute, please. Sorry about that. All right, let's start. This used to be the most popular question that came out in Newton's laws, inclined planes, until the examiner realized that learners were becoming experts in inclined planes, and then they started changing the question to all these other fancier ones. But this was actually one of the best questions they could get. Please look at the question carefully. Look at the direction in which the object is moving, because it's going to affect your frictional forces on both these masses. Right, what do we have here firstly? Normally, when we're dealing with inclined planes, both the masses are on an inclined plane. But here, I think it's kind of easy. One mass is on a flat surface. What does that mean? It means for this mass here, the gravitational force is not broken up into components because it's acting straight down along the y-axis. Your normal force is upwards. I'm guessing, I didn't read the question. We're going to have a kinetic frictional force acting that way. Now, how do I know it's that way? Because they gave us the direction of motion of the 3 kilogram. If the 3 kilogram is going downwards, that means quite simply the 5 kilogram is moving across to the right. And because it's accelerating to the right, the frictional force is to the left. And your tension in your string is going to be away from the mass or towards the pulley. And those are the 4 forces there. What you then need to realize is that for the 3 kilogram that is on the inclined plane, you're going to break up your gravitational force into components. And that's the other reason I chose this example. I wanted you to realize that when an object is on a flat surface, the gravitational force remains vertically downwards with no components attached to it. But when a mass is on an inclined plane, this same gravitational force is then broken up, and I'm going to put this in green, into FG perpendicular here. And FG parallel here. Your parallel component, by the way, always acts down the slope. Your normal is going to be in line with your FG perpendicular. Your tension along the string away from the mass, it's the same tension there and there. And because it's going down the incline, it's accelerating downwards, your kinetic frictional force is going to be upwards. Now that's the big difference between a flat surface against an inclined plane. Again, it's this here. The component of the gravitational force. All right, let's read now. Two blocks of masses 5 kilograms and 3 kilograms respectively are connected by a light inextensible string that runs over a light frictionless pulley as shown in the diagram below. The 5 kilogram block experiences a kinetic frictional force of 8 newtons. So that's 8 newtons there. The coefficient of kinetic friction between the 3 kilogram block and the surface. So here they gave us the mu k. If they gave us the mu k, we'll have to calculate the frictional force. That's 0.15. Remember, to get the kinetic frictional force, we need the normal, but your normal is going to equal to Fg perpendicular here. Not Fg, Fg perpendicular. Eh? So question 2, define frictional force. Please learn your definitions. I'm not a fan of knowing all the definitions off by heart. Draw a labeled free body diagram of the 3 kilogram and indicate all the forces acting on the block. So I'm going to just quickly do that again for you. You are not allowed to show the incline, but I'm going to draw it here. And here's my mass. Fg perpendicular. Fg parallel. Your normal. Tension. Kinetic friction. And remember, it's accelerating downwards. Then for the other one, I'm just going to leave that there on the top. I'm just going to save myself a bit of time because I think I'm going to run out of time here. Calculate the magnitude of the frictional force acting on the 3 kilogram block. As I said, they gave us the mu k. So we're going to use our Fk formula to calculate the kinetic frictional force. So 2.3.1 Fk equals to mu k multiplied by the normal. And again, your normal here is equal to Fg perpendicular. What's the formula for Fg perpendicular, anyone?
So mg cos theta.
mg cos theta.
You need to remember this off by heart. It's not on your data sheet, eh? And Fg parallel is mg sine theta. So your kinetic frictional force here is going to be mu k. The normal is equal to Fg perpendicular. Fg perpendicular is mg cos theta. So that's going to be 0.15 into 3 times 9.8 cos 30. Answer?
So 3.82.
3.82.
82, sir. Yes.
Okay. Once we got that, we're going to find the magnitude of the tension in the string. Please note, we don't know the acceleration. So we're going to eliminate the acceleration and get T directly here. So 2.3.2. I'm going to start off with our mass on the inclined plane, which is the 3 kilogram mass. And for the 3 kilogram mass, we're going to go F net equals MA. My F net for the 3 kilogram mass is this positive force plus these two negative forces there. So it's going to be Fg parallel plus minus my tension plus minus my kinetic friction is equal to MA. So My FG parallel over here is going to be mg sine theta minus my tension minus my kinetic friction is equal to ma. My mass is 3 times 9.8 sine 30 minus the tension. Kinetic friction is 3.82 equals to 3a. 3 times 9.8 sine 30, someone? Minus the 3.82 as well. Do these two together.
10,88.
Thank you. Minus the ft equals 3a. I'm going to leave this as equation 1. Then the other one on the top, oh shucks, man, is the 5 kilogram. Here, it's going to be t minus the fk there. So for the 5 kilogram, F net equals ma again. It's T plus minus your kinetic friction equals to ma. We don't know the tension. They gave us the kinetic friction to be 8. Your mass is 5, and we don't know the acceleration. It's a. Please watch what we do now. It's a bit of a nasty set of equations. Why? Because I got 3a here and I got 5a there. So I'm going to multiply the top equation by 5. I want to get 15a here. I'm going to multiply the bottom equation by 3. 3 times 5 is 15a. I'm going to get 15a and I'm going to solve for t. Multiply 10.88 by 5. Someone quickly, please.
54,4.
Thank you. Minus 5 ft equals 15a. So there's your new equation 1. And multiply the bottom one by 3. 3t minus 24 equals 15a. There's your new equation 2. You got 2 equations for 15a. So 54.4 minus 5 ft will equal to 3t minus 24. Gonna squeeze it here. 54,4 minus 5 ft equals to 3t minus 24. Take the minus 5t across, you're going to get 8t. 54,4 plus 24 at the end there. 54 plus 24, 78.4. 78.4 divided by 8.
9,8.
Yeah, nice value. And there we are. Our first question on inclined planes. And again, they said very nicely here, magnitude of the tension, magnitude of the friction. What people, please check your respective groups if I'm up for it, because I've got a pretty long evening to go through. I'll send you a message about 9:30 to let you know whether we're going to have a lesson tomorrow. Please don't be asleep by 9:30. Thanks for attending, everyone. We may meet tomorrow morning. There's no lesson at 8 p.m. tonight, eh?
Thank you, sir.
All right, guys, no problem.
So, one more thing about circuits this year.
Yes, sir.
Is it
Yeah.
is it going to differ from last year?
Yeah, it is. There's internal resistance, but I think I did internal resistance with some of you last year already. So there's no difference between last year's work and this year's work. In other words, we did it all last year.
Okay, and what about electrostatics?
There's no difference. It's exactly the same, but it's a really hard section. So I would say that you guys should actually attend that. Electrostatics was just horrible. So I think all
12
the grade
hours.
should actually attend it because it'll be your first opportunity to do some revision in electrostatics anyway. So I'm going to actually put up a notice on the group that everyone should attend it this week with the grade 11s.
So you said on Friday, right?
Yeah, definitely on Friday, but it'll be a bit of an awkward, weird time on Friday. So just check up.
Okay. Thank you, sir.
Right.
Snaps.
See you guys. Snap.